In the previous video, we looked at an example involving exponential growth and decay. However, real-life examples often have a little bit more to them. So, for example 3, we're going to look at Newton's law of cooling, where an object cools but doesn't approach zero, but rather the room temperature that the object is in. This adds a little bit extra to our equations. Objects lose heat according to this law. T, so that's a bit confusing, capital T is for temperature, lowercase t for time, equals K, that's our constant, outside of T minus T1. So notice this time it's not just K times the quantity, but rather there is some other constant value in this question, in this equation. In other words, the room temperature for what we'll be looking at. Now, since the object is cooling down, this is exponential decay, and so our K value is going to be negative. If we think ahead to what the solution will be, we can go back to our exponential growth and decay from last lesson and just modify it a touch. So our temperature will be equal to some constant times e to the power of kt, but the very fact that we have this extra constant in our differential equation means that shows up in our solution. So let's think about what's happening here graphically. Exponential decay means that we're going to head down this way, right? A negative k value in our power means we've got our exponential curve flipped about the y-axis, or in this case the temperature axis. However, this constant value lifts our graph up. So we have some room temperature and our graph will approach this, like so. Okay, so let's get into our example that deals with Newton's law of cooling. An object is heated to 320 degrees Celsius, then left to cool. The temperature in the room is 26 degrees. Part A, if the temperature of the object is down to 290 degrees after 10 minutes, find its temperature after 30 minutes. Now, first thing to be aware of is this 26 degrees. This is going to be our T1 value. This is the constant temperature, the room temperature that our object will approach. So it's not going to approach zero, it's going to approach this 26 degrees. Okay, so how do we start part A? Well, we can start with the differential equation. So the rate of change of temperature with respect to time is equal to some constant value. Now we know this K value will be negative, right, when we get down to it. And it's T minus T1, but in this case, we know that T1 is 26. Okay, so remember what we're trying to find, a temperature. So we need our solution to have capital T as its subject. However, for now, we need to integrate with respect to temperature. So we need to flip both sides. And then we'll be able to integrate with respect to capital T. So what does that leave us with on the left? Well, just little t for time. And on the right hand side we have a constant 1 on k. We can bring that out the front to make life a little easier. And after the integral sign we are left with 1 over capital T minus 26. So what happens when we integrate here? Well, it's essentially a 1 on t question, isn't it? In this case it's very similar to just 1 on t because the derivative of t minus 26 is just 1. So there's nothing we need to adjust here in order to integrate. So we're going to get the natural log and our absolute values, and in this case it'll be t minus 26. Right, if you've got any concerns about that, just integrate this guy here. Differentiate this guy here, and you'll go back to this function. Now we'll keep the absolute values in place for now. But remember, we've got time as the subject and we want temperature as the subject. So we need to go about the business of rearranging. So first we'll take the constant of integration over to the other side. And then we can multiply by this constant, k. And if we expand the left-hand side, we get kt minus kc. Now that's just going to be some other constant, but we'll leave it as kc for now. And then how do we undo the natural log? Well, we take the exponential base e of both sides. And over here, because we're dealing with an exponential where we know it'll all be positive, now we can forget about the absolute values. That'll come out in the wash anyway, even if we left them there. Let's go back to the left-hand side. What's happening here? So this is just some other constant, right? So remember when we split this into e to the kt times e, the plus or minus doesn't really matter here because it's some constant value. So we can sort of get rid of it if we like. I mean, if we kept it and thought of it as a division question, it wouldn't matter so much, because ultimately whatever this constant value is, we can just call it something else. Right. Now we still have our t minus 26, but if we want to get temperature by itself, we're going to add the 26 to both sides. And so this matches up with the form that we were talking about earlier. We still have some constant values, a and k, here that we want to actually figure out what they are. So we can use the initial information provided in the question. The first bit of information we were given was that at time equals 0, or initially, the temperature is 320 degrees. Right, so that's what the object started at. So substituting that information in, what's going to happen? Well, 320 is the temperature of the object. We've got our 26 degrees, and a times e to the power of 0. K times 0 will be 0. And so e to the power of 0 is just 1. And so we get that a is 320 minus this 26. That gives us 294. So there's our a value. But we were also given some other information. We were told that after 10 minutes, the temperature of the object had dropped to 290. So substituting this information in, we get 290 equal to 26. Now instead of a, we can actually put in 294 this time, and that's times e to the power of kt. Now t is time, and so we can put 10 in there. So now we have everything we need to solve for k. So let's aim to get k by itself. First of all, we can subtract the 26 from both sides. So that leaves us with 264 on the left. And then we can also divide both sides by 294. So I might do that now. And on the right, we are now just left with e to the power of 10k. Taking the natural log of both sides will leave us with just 10k. Do a little switch. And when we divide by 10, we'll get our answer. Now I want you to think about this fraction here, 264 over 294. Is it greater than or less than 1? Okay, it's less than 1. We know that log of anything less than 1 is actually going to give us a negative value. So we shouldn't be surprised that when we plug this into the calculator, we get a negative value, but that makes sense because we're dealing with exponential decay. So when we substitute into the calculator, we get minus 0.0108. And there's our k value. So that means that we can finalize our solution to be t equal to 26 plus 294 times e to the power, and we actually have our k value. Okay, what did the question ask us? The question actually wanted a temperature after 30 minutes. So let's substitute in time, little t, equals 30. So when t equals 30, our temperature will be 26 plus 294 times e to the power of our k value multiplied by 30. This is just another job for the calculator, and when we plug that in, we get 238.9. So our temperature is going to be 238.9 degrees Celsius after 30 minutes. And there's our answer for part A. Let's go on to part B. Show that the final temperature of the object is 26 degrees. So in this case, we have to understand that when they're talking about final temperature, we have to think what happens after a long time as t approaches infinity, essentially. So let's rewrite our formula that we came up with. T equals 26 plus 294 times e to the power of our k value, that very little negative value, times t. Okay, so what's going to happen as time goes on and as it approaches infinity? So think about this exponential value. Remember, we've talked about how when we're dealing with exponential decay, our value approaches 0 as time goes on. So we can state that this value here is going to approach 0. That's going to approach 0. So what does that mean? Well, if this is approaching 0, then 294 times that will still approach 0, and therefore the overall temperature will just approach the 26 value, which is left. Now, if we plugged in any actual time value, no matter how big it is, we will still get a tiny little value from this bit. So technically, we'll never actually see a point where we get 26 in this model, but it approaches 26. And so for all practical purposes, we can state that the temperature will eventually reach 26 degrees. So eventually it'll get there. And that is our example on Newton's law of cooling. Good job, everyone.